Hi everyone, I'm Sir Mel and welcome to Mathematics in the Modern World. If you are new to my email channel, please don't forget to subscribe and click the bell button for more notifications. Today we're going to have a quick review about the four basic concepts in mathematics. Shall we start with the first, the set? I have here the first five terms. Finite set, that contains elements that can be counted or terminates as a certain number or word. Otherwise, we call it as infinite. The keyword if the set contains of three dots or what we call ellipses. But if the set has no element at all, we call it as null or empty set. However, if the set contains exactly one element, we call it as single tone. On the other hand, if the set contains of all elements, then we call it as universal set and it is denoted by capital U. Now let us have the other five terms. First is equal set. When the set of all or two or more elements have the same number of elements as well as the elements itself, we call it as equal set. However, if the two or more sets have only the same in terms of the number of elements, we call it as equivalent set. In short, all equal sets are equivalent sets, but not all equivalent sets are equal sets. Now let's proceed with the subsets. It is a set generates from the original set. When we say cardinality, it talks about the number of unique or distinct elements in a given set. But when we say power set, it's like subsets because it is the family of all subsets in a given set. Now let us have the specifications of set. We have rooster method or listing notation. We have rule method, predicate or set builder notation. And the last is recursive. Now let us have this example. Let's set A is a vowel in an English alphabet. We know that in an English alphabet, we have vowels A, E, O, U. Now, when we say rooster method, we're going to put all the elements in braces and separated it by commas. But in the rule method, we're going to use variable to represent the elements and the slash that indicates such that. Read as set A has the set of all x such that x is a vowel in an English alphabet. But in the recursive rule, it is a set defines or generates its members such that A is an element of set A that has elements A, E, O, U, which is true. Now let's proceed with the operation on sets. So let us have these four diagrams or figures. So first figure, as you observe that the set A and set B are all shaded region. We call it as union. But on the second, the only shaded region is in the middle of set A and set B. We call it as intersection. On the third diagram, the only shaded is the set A, but the whole set B are not shaded, included the middle. We call it as set difference. And last, as you can see, the set A has no shaded, but the shaded region are from the outside of the set A, which is shaded region on the universal set. We call it as complement. Now, in this next slide, we're going to use the operation on sets to have a clear idea about this. So let us have this number one problem. So as you can see, given our universal 1 to 9, we have set A 2, 4, 6, 8, set B 1, 3, 4, 6, 7, 8, set C has 2, 3, 5, 7, and set D has 5, 7. We're going to find the set B union to set A union to set D. In our previous ideas, when we say union, simply combine, unite, or put them together all the given elements. So in this case, I am going to discuss to you on how to provide a solution step by step. First, if we have series or more operation in a given problem, we're going to solve it from left to right. In short, we're going to do first operation on set B union to set A. So we have this. So bring down all the elements of set B, bring down all the elements of set A, as well as the operation. So since union means to unite, we're going to unite them all. So we have this 1, 2, 3, 4, 6, 7, 8. First set of elements. Now let us proceed to the next operation, which is still unions. So we're going to enclose the set B union to set A so that we have already done solving it and proceed with the next operation. So we have this now. So set B union set A union to set D. Bring down the first answer, then bring down as well the next operation. So again, the keyword is to unite. Put them together or to combine all the given elements in this problem. So the final answer is 1, 2, 3, 4, 6, 7, 8. That is how we're able to get this operation in problem number 1. Now let's proceed with the given number 2. The same given, but the question is, we're going to find the set B intersect to set C intersect to set A. Again, in order to solve this properly, we're going to start it from left to right. So shall we start the solution to set B intersect to set C? Bring down all the elements of set B as well as the set C we have here and the operation. So the keyword for the intersection is their common elements. Now let us evaluate all the elements in set B and set C. So what do you think are the elements which are present in both sets? So here we have 3, 7, and the other has also 3, 7. Therefore, the answer is 3, 7. Now, the same process, we're going to enclose the first process and extend it to the next operation. So we have now like this. So bring down the 3, 7 and bring down the set of A, 2, 4, 6, 8. Now, the keyword for intersection is their common element or elements. Now, observe the first set and the second set. Evidently, it has no common element. So therefore, what is your answer? The answer is null set or empty set. So that is how you're able to get the problem number 2. Now let's proceed with the problem number 3. The same given. The question is, find the set universal set, set difference to set D, set difference to set C, and set difference to set A. We have 4 sets here. Again, the process to solve it properly is from left to right. So let us bring down the first 2 sets with the operation set difference. Okay, the solution is like this. Okay, we're going to bring down all the elements of the universal set minus or set difference to elements of set D. Now when we say set difference, the keyword is the difference, especially from the first set to the other set. So you're going to observe what are the element or elements that are not present to the other set. So in this case, we have 5, 7. So 5, 7 is present on set D. Therefore, we're going to bring down everything except to 5, 7. So we have now here 1, 2, 3, 4, 6, 8, 9. Now let's proceed with the next set, which is set difference to C. Enclose them and we have like this. Bring down the first answer and then bring down the elements of set C. The same process, we're going to see the first set compared to the second set, which is not present on the second set. So we're going to bring down all the elements of set A, the first set, except to 2, 3, 5, 7, if ever. So since 2, 3 are present, so bring down 1, 4, 6, 8, 9. So we have now 1, 4, 6, 8, 9. The same process, left to right. So we're going to enclose the first 3 sets like that and bring down the last operation and the set. So bring down the first answer and then bring down all the elements of set A. The same, If ever 2, 4, 6, 8 are present on the first set, then we are not going to include them. Otherwise, those elements are not present to the second set would be our answer. Since 4, 6, and 8 are present in both sets, so our answer must be 1, 9. So the final answer is 1, 9. That is how we get the set difference of more than 2 sets problem. Okay, so I hope you able to manage to come to follow all the steps by steps. Okay, so let's proceed with the last problem. The same given, but we're going to find the complement of A, the prime of A. So when we say complement, from the root word to complete, basically we're going to look again to the universal set. So this is how we're going to solve it. First is we need to bring down the set A for us to have a clear idea. Then after that, we're going to put the complement, and that looks like. Then when we say complement, we're going to complete A, and of course our basis is in the universal set. So what do you think would be the elements to complete the set A? So let's look back with the universal set. So right now we have 1, 3, 5, 7, 9 would be the elements to complete the set A. Okay, so I hope you have a clear understanding about the operations on set. Okay, that ends about the different types of set. Now let us proceed with the second and third basic concepts in mathematics. And these are function and relation. In a simple way, we can determine that the given is a function when the elements of the domain pairs at exactly one element from a second set called the range, while the relation when the elements of the domain pairs with one or more elements from a second set called the range. Now let us have the illustration for us to see the relationships between function and relation. So we have here 5 illustrations. On the first figure, we can see that there is a curve. We have also line and circle. So that is by graph. Second, we have letters, number, variables, expression, or term. We call it as by equation. Third, we have numbers corresponds to the letters. We call it as by mapping. Fourth, we have two numbers inside the parentheses in a given set. We call it as by ordered pair. And last, we have different values inside the box. We call it as by table. Now, we're going to discuss it one by one so that we're able to show to you the different relationships or different forms or ways to tell the relationships of function to relation. So shall we start with the graph? Okay, I have here 4 graphs. Now let us try to evaluate each and try to know whether it is a function or just a relation. So we're going to use the VLT as vertical line test. It is a test to apply to all graphs in order to know whether the graph is a function or just a relation. So let us try to draw it in the first figure. So as you can see, the VLT intersect more than one in a given figure. So according to the function, if the vertical line test intersect at exactly 1 in a given graph, then it is a function. In this case, it intersect more than 1, so it is a relation. Let us try to apply VLT on the second figure. So as you can see, VLT intersect at exactly 1 point, so it is a function. The third, we observe that the VLT intersect twice in the given figure, so it is a relation. On the last, we have the VLT intersect still on the 2 points of a given graph, so it is a relation. So remember, in graph, we can tell whether it is a function or just a relation by simply applying the VLT or vertical line test. Now let us proceed on the other illustration, that is by equation, by table, and by ordered pair. So let us have the first equation. We have y equals x plus 1. In this moment, we don't know yet if it is a function or just a relation. So let us try to do the process. So after by equation, let us have by table. Now as you can see, we have x and we have y. In this particular situation, we can assign the values for x since x is an independent variable, which means we can assume values for it so that we can define y since y is a dependent variable. So let us try to evaluate it by substitution. Let's say we have -2, the value of x, substitute here. So -2 plus 1 equals -1. The same process. -1 plus 1 is 0. 0 plus 1 is 1. 1 plus 1 is 2. And 5 plus 1 is 6. So we have now points or values for x and the y. We can use it to produce an ordered pairs. So we have -2, -1 here, -1, 0, 0, 1, 1, 2, and 5, 6. So, but in this moment, we cannot tell yet if it is a function or just a relation. Earlier, we know that a graph is a function or a relation by the use of PLT. So, let us try to use the values on the table or the ordered pair to illustrate it in a graph. So, we have now this. So this line is what we call the equation y equals x plus 1. So since it is a line, so it is a linear equation. Now let us apply VLT here. Okay, so we found out that the VLT intersect at exactly one point. That makes this equation as a function. Now, without looking in this graph, simply looking with the values on the given x or given ordered pair. So let us try to tell whether it is a function or just a relation. Now, according to the definition of function, that the domain should or must pair at exactly one element on the second set, the range. So in short, there should no two the same x elements in a given table or ordered pair, or else it becomes a relation. So since -2, -1, 0, 1, 5 are not identical, they are unique and distinct to each other, then this is a function. The same as here in the ordered pairs. So -2 is different from -1, 0, and 1, 5. So they are distinct and unique to each other. So that makes this table equation as well as the graph and the ordered pair as a function. Now let us move with the second equation. So we have y equals absolute value of x minus 2. Okay, let us do the same process. So we're going to have by table. Now, again, x can be assigned. So it's better to have negative, 0, and positive. So in order to get the y, we need to substitute -2 to this value. So we know when we say absolute value, we're going to change everything into positive. So -2 becomes +2 minus 2 equals 0. Okay, -1 becomes +1, minus 2 equals -1. 0 minus 2 equals -2. 1 minus 2 is -1, and 5 minus 2 is +3. Now let us use this to create the ordered pairs. So same like that, and 5, 3 the last. Now, based on our notion earlier that we can tell the table or the values of the table and the values of the ordered pairs can be easily detect whether it is a function or just a relation by looking simply on the values. So as you can see, -2, -1, 0, 1, 5 are not identical. They are unique and distinct to each other. So it is a function as well as in the ordered pair. So this equation, the absolute value equation, is a function. But we need to graph it. So the picture of graph is like this. If we try to apply VLT here, okay, as you can see, VLT intersect at exactly one point. That makes this equation as a function. Okay, let us have the last example for by equation, by table, and ordered pair. So let us have this equation, x equals y squared minus 3. This time, we are going to change the independent and dependent variable. So we're going to use y as the independent variable. So we're going to assign values for y to get the values for x according to the given equation. So let's say we have y negative 2. We know negative 2 itself is positive 4, minus 3 is 1. Okay, negative 1 itself is positive 1, minus 3 equals negative 2. 0 itself is 0, minus 3 is negative 3. 1 itself is 1, minus 3 is negative 2. And 3 itself is 9, minus 3 is 6. Okay, so let us use this to have the ordered pairs. Okay, now we're going to plot this table, or points of table, as well as the ordered pair into the Cartesian plane by Rene Descartes. So we have like this. So obviously, if we try to use VLT here, okay, VLT, vertical line test intersect more than one. So which means this equation, this table, as well as the ordered pair and the graph is what we call a relation. Okay, now by simply looking with the values on the given table as well in the ordered pairs. So let us try to look with the values of x. 1, negative 2, negative 3, negative 2, and 6. As you observe, there are two negative 2 here, meaning to say the domain, the elements in the domain repeats more than one. So that makes it as a relation. The same as in the ordered pair. Okay, so that are some of the examples to show to you the relationship of function and relation by graph, by equation, by table, and by ordered pair. Now let us proceed to the last illustration, and that is by mapping. Now as you can see, we have two variables here, the x and the y, that contains different elements, or the same elements rather. So we have 1, 2, 3, 4, 1, 2, 3, 4. Now the x corresponds to another one. The x has 2 corresponds to 3, and 3 corresponds to 2, 4 corresponds to 4. So we have now an ordered pair, 1, 1, 2, 3, 3, 2, 4, 4. Now according to our previous idea that we can tell whether it is a function or just a relation by simply looking with the domain or the first element. So since 1, 2, 3, 4 are unique, distinct to each other, then it is a function. But how do you call it by mapping? Since one corresponds to another one, exact one, another exact one, exact two, another exact three. So it's only 1 to 1. So which means it is a 1-to-1 correspondence. Okay, let us go to the next by mapping. So as you can see, the elements of x, negative 2, 0, 4, 7, elements of y, negative 7, negative 4, 3, and 8. So let us do the correspondence here. Negative 2 pairs with negative 7 as well. Negative 2 pairs to negative 4. 0 pair to 3, 4 pairs to negative 4, and 7 pairs to 8. So let us have the ordered pair. Let us evaluate the ordered pair. Now, since negative 2 repeats more than 1, then this is what we call a relation. Okay, so how do you call a type of by mapping is this? So since this negative 2 pairs more than 1, so this one pairs too many, so we call it as one-to-many correspondence. Okay, so let us now go with the third. So in this, we have the elements of x, 2, 3, 5, 7. We have elements of y, 1, 3, 5, 7. Let us try to correspond them or pair them. So 2 pairs with 3, as well 3 pairs with 3. So 2, 3 shares with the range of 3. 5 pair with 5, 7 pairs with 7. So we have now the ordered pair 2, 3, 3, 3, 5, 5, 7, 7. Now let us try to look with the first elements, the x or the domain. Does the domain repeats more than 1? 2, 3, 5, 7 is not. Therefore, it is a function. But let us try to see the characteristic of the correspondence. So 2 corresponds to 3, 3 corresponds to 3. So there are many y's going to what we call this as many to 1. Many y's down to or pairs with the x. Many to 1 correspondence. So it is a function. Last, we have this letter D by mapping. So the elements of x are 0, 2, 4, 6. Elements of y are 0, 3, 5, 7. Now, 0 pairs with 0, 2 pairs with 0, 4 pairs with 3, and 4 pairs with 5, 6 pairs with 7. So as you can see, 0 and 2 shares a pair in the range as 0, and 3 and 5 share the same elements on the domain, which is 4. So we have this kind of ordered pair 0, 2, 4, 4, 6 according to the function. If the domains repeat more than 1, then it's not a function. It's just a relation. In this sense, 0, 0, 0, 2, 0, 4, 3, 4, 5, 6, 7. So 4, 4 repeats more than 1 on the domain, then this is a relation. But what kind of by mapping is this? So since 0 to many shares 1 here, and 3, 5 many shares 1 here, so we call it as many to many correspondence. So these are the 5 different ways to illustrate relationships between function and relation. I hope everything is clear. Now let us proceed with the last basic concepts in mathematics, and we call it as binary operation. So when we say binary operation, it is an operation that takes two input elements from a set and gives a unique result that also belongs to the same set. So meaning to say, from the word by, which means two, we're going to use that two elements in a given set to produce another element in a given set. So we call it as binary operation. So let us have the different types of binary operation. The commutative. So a binary operation denoted by this asterisk on a set A is commutative. So in this case, if A binary operation B equals to B binary operation A, for all ordered pair AB, element of set A were in non-empty set. So let us try to say that this binary operation is addition. And let us assume that A equals to 8 and B equals to 9. So when we add 8 plus 9 becomes 17. And the sum of 9 plus 8 or 9 and 8 is also 17. So meaning to say, whether we rearrange the addends, then still give the same sum. That makes them commutative. Let's proceed. Associative. The associative property of binary operation hold if for a non-empty set A, we can write group of binary operation A, B, binary operation C equals to A binary operation of the group B binary operation C. Let us have in natural numbers. So we're going to change the binary operation into multiplication. Let's say we have A equals to 4, B equals to 5, and C equals to 6. So by binary operation, under the multiplication, so we are going to A times B group times C equals 120, since 4 times 5 is 20 times 6 is 120. The same as if we regroup 5 times 6 is 30 times 4 still 120. That makes them associative. As you can see, the regrouping of the addends, the multiplicants or multiplier gives the same product. So that is associative property under the multiplication. Let's proceed. Distributive property. Let binary operation and the of symbols be two binary operations defined on a non-empty set A. The binary operations are distributive if a binary operation of B of C, okay, we read that is as of, okay, A binary operation B of A binary operation C, or B of C binary operation A equals to B binary operation A of C binary operation A. Consider that this asterisk to be multiplication and this of become subtraction. So following this condition, so since we have A equals to 2, B equals to 5, C equals to 4. Now this is for multiplication and the other is for subtraction here. Okay, so let us try to change. So from binary operation becomes times, from of becomes minus. So we're going to try if the product and the difference are equal. If equal, then they are distributive. So substitute everything. 2 times 5 minus 4. 5 minus 4 is 1 times 2 is 2. We have 2. Okay, here we have A times B minus A times C. So 2 times 5 minus 2 times 4. We have 10 minus 8 equals 2. They have the same answer. Meaning to say, this binary operation under multiplication and of under subtraction is what we call distributive property. Okay, so let us now proceed. Inverse. If a binary operation symbol on a set A which satisfy A binary operation B equals to B binary operation A, which is E, which means inverse for all A, for all A, B is an element of set A. So the inverse of A is invertible if for A binary operation B equals to B binary operation A equals to E, which is identity. So inverse of A equals to B. So 1 is invertible when the binary operation is multiplication. Simple as if you are going to multiply 2 to its inverse, like as 2 times 1 half, the answer is identity, which is 1. Okay, so now let us have a problem about binary operation. So let's have A binary operation B equals 3A plus B. So again, by definition, it is a set of calculation involving two elements to produce another set, okay, or elements in a given set. So A binary operation B produce another element in a given set. So let us try to find 2 binary operation 5. So how? This is now the solution. Okay, so A becomes 2, B becomes 5, and follow everything. So we have now, this is for the A, this is for the B. Now let us substitute all the A by 2 and all the B by 5. So we have 3 times 2 plus 5 equals 6 plus 5 equals 11. So the binary operation of A to B equals 3A plus B, which is finding the 2 binary operation 5. The answer is 11. Okay, so therefore 2 binary operation of 5 equals 11 with regard to the given binary operation. Okay, let's move. Let us have the second problem. Let A binary operation B equals 3A plus B. Is A binary operation B commutative? Now, with the use of this set, okay, according to binary operation, on the set calculation involving two elements in the set to produce another element which also in the given set. So we're going to have verify that A binary operation B equals B binary operation A of the word commutative. So let us have the 3A as A, B as, 3A this time, then later B becomes DA. Okay, so we have now 3A plus B, 3B plus A because of the commutative. So not true for all real numbers. Okay, how and why? So let us assume A is 2, 3 is B, then 3 times 2 plus 3 equals 3 times 3 plus 2. So since we have 3 times A is 2, B is 3, then 3 times the B is 3 plus A is 2. So we know 3 times 2 plus 3 is 9. 3 times 3 plus 2 is 11. Are they equal? No, of course. So meaning to say, this operation, binary operation, is not commutative. So not true for all real numbers. Okay, so that's all. Now let's move with the last example about binary operation. Given the ordered pair, so let A binary operation B equals 4B minus 3A. So this time, we have negative 3 binary operation 2. So the solution is A become the 3, 2 become the B. So all the A changes into negative 3, all B changes to positive 2. So we have now negative 3 binary operation 2 equals 4 times 2, 3 times negative 3. Okay, simple arithmetic. So we have 8 plus 9 equals 17. Negative times negative is positive, so it becomes 9. So 8 plus 9 is 17. Therefore, negative 3 binary operation to 2 equals positive 17 in a given binary operation. Okay, so binary operation can also apply in a given table. So here we have the binary operation 1, 2, 3, 4 and all the elements inside this box or this table with 1, 2, 3, 4, 5 by 5. Okay, right now we're going to find what is for binary operation 3. Okay, so when we say for binary operation 3 using the table, we're going to use like an intersection. So the first value is for the row. The second value is for the column. So here, fourth row, third column. So for third, we have 3. The answer is 3. That is how simple to answer the binary operation on a given table. Let us have another. What is 2 binary operation 1 group? Binary operation 3. So we have first, left to right, since there are many numbers or many binary operation involved here. So left to right, follow also the parentheses. So 2 binary operation 1 is 3. So bring down 3. So 2 binary operation 1 is 3. Then 3 binary operation 3 is 1. So therefore our answer is 1. Okay, thank you and God bless everyone.